Okay, so this is 10.2 and it's called the unit circle and the coordinate plane. Today is Wednesday, May 5th, and just kind of reminding you that it always helps to check Michigan Virtual first or after you look through the lesson that we cover together. So this video lesson will kind of zero in on the things that are on the 10.2 quiz. It will not cover every single thing that's mentioned in 10.2 that Michigan Virtual shows. So it does help I'll give you a couple of bullet points just to kind of, just remind you that you should be kind of getting more detail, especially for those of you moving on to pre-calc and honors pre-calc next year. You don't want to just, do the bare minimum of what we cover here because you would have kind of some missing pieces then. So really consider kind of looking through that lesson, try the practice problems, watch the videos, do all of that in addition to this overview that I'll give you today. So I know that Michigan Virtual starts off 10.2 with describing two trig functions specifically. These trigonometric functions are called sine and cosine, things that you've definitely seen before, especially in geometry, but it was taught in geometry at the end of last year. So because of like how we were sent home from school and everything was kind of emailed, the lessons were, video lessons sent to you, it wasn't live. I know that some of that can seem a little bit, you might not remember it as much. So we'll cover a lot of that as if you kind of don't know it exactly. So basically, Michigan Virtual shows that sine and cosine have these curves, or like they're graphs. It shows how they curve up and down, and it continues that way based on the unit circle. So what it shows us is it starts showing that the x value when dealing with the unit circle, it was whenever you found what cosine of theta was, and we talked about a little bit about theta yesterday, how it was based on the angle that is showing like where that terminal side would go when you're working with the unit circle. Same for y, it was showing sine theta. And so if you have an x and you have a y, that's like the coordinates of x and y, x comma y, are on the unit circle. So like if you had a point on the unit circle, I'm just going to make a hypothetical point like 2, 5 or something like that. If that point was on the unit circle, like the actual circle where the radius is 1, that's what unit circle will represent, then you would be able to find cosine of an angle and it would equal the x value, and sine of that same angle would equal the y value. And again, it shows some more examples specifically with using the angle measures that are on the unit circle. So for example, cosine of 90 degrees, you could use a calculator and calculate that, and I'll show you how we can do that just briefly today. Same thing for sine of, say, 90 degrees. That would help you figure out what are the x and y values, and you could then plot the points that are on the unit circle. So we're not going to spend too much time with that because, again, it was not on the quiz or the test. I want to make sure we get time for the examples that are on there. The other thing that Michigan Virtual practices quite a bit is, and then this is a good idea to practice with it, is some calculator practice of how to find sine of an angle, or cosine of an angle. And again, it'll talk more about what cosine and sine are, and I'll give you more of an idea in just a minute too. So sine of an angle, cosine of an angle, making sure you're using the correct degree or radian mode. So we'll talk a little bit about this right now, but basically checking degree or radian mode. RAD for radian. And so just making sure that you kind of work through both of those. Now there's also some tangent, TAN is tangent or tan. They kind of introduce tangent as well somewhere. So it includes tan. Okay, so I will just show you one quick thing on the graphing calculator in case you don't know how to do this yet. And Michigan Virtual, again, it will explain it further too. And that's how to, on a graphing calculator, how to figure out which mode you're in for degree versus radian. If you have a scientific calculator, which I don't have one, with me at this moment, but you can instead look for the buttons for mode anywhere. It's usually towards the top, usually, and then again, depending on the scientific calculator you have, it may change. For a graphing calculator, the mode button is right in the top, like below this row, of course, but next to the second button. So you're going to press that mode button, and you're going to just move your cursor down, the down arrow 3 times, or 2 times actually, just to get it to the third blank there, and you can see it blinking on radian, or if I go to the right arrow, then it blinks on degree. So depending on what we're working with, if you're working with degrees, if the problem gave you a degree measure with like the little degree symbol, then you would press enter and it would change it to degree, keep blinking there. Or if it was radian, you could hit enter and it would be in radians, where it's dealing with pi and or just numbers that don't have a degree symbol, right? So like, let's say I did want to do it in degree, I could then, get out of this menu or the mode. If you're ever unsure, if you go back to mode, then you'll see which one you had chosen. So I, again, was in degree mode. But once I hit clear, I'm back to my main page, and I can find the sine or cosine of something. So for example, say I want to know what the sine of 90 degrees is, which we know that on the unit circle, that's like straight up on the y-axis. And notice I get 1 for an answer, which makes sense because my radius is 1 in a unit circle. I could do the same thing for cosine of 90. And the reason the answer comes out to 0 here is because, again, the 0.01 is like what we talked about, the x and the y, that would be a point on there. I could also look at tan, and it gives me, it does not give me an answer there. And if you think about why that's the case, it's because tangent is sine over cosine, and I can't have 0 in the denominator there. So I'm not able to find tangent of this angle, and that's okay. Sometimes something is undefined. So that's a little bit about using the graphing calculator. Again, Michigan Virtual explains it in much more detail. Let's go ahead and move on to what's on the quiz and eventually on the test. So the first thing we need to kind of remind ourselves of is that there are 6 trigonometric functions. The ones you're most commonly probably remember from geometry, or even before geometry, because it's covered even middle school and things like that sometimes, is the three that I just kind of mentioned earlier: sine, cosine, and tangent. So off to the side here, I'm going to go ahead and write them. Sine, this is like the full word, and we will abbreviate here in just a minute. Cosine is the next one. And then tangent. Those 3 are the most common ones that we're used to seeing. Then there are reciprocal trig functions, where we take the reciprocal of each of these. And so sine's reciprocal is called cosecant. So I'll just kind of put an arrow there and show you that it's called cosecant. Cosines is called secant, and then tangent is called cotangent. So of those 3, just a reminder here, though, that Michigan Virtual, for some reason, kind of puts these in a different order. It puts secant, and then cosecant. It doesn't say that they are the inverses. I just don't like the order that they put them in. I would put them in this order because it kind of shows you exactly which one, and it's reciprocal. So let's go ahead and write down the most common ones. Think of that mnemonic device you may have learned, which is called SOHCAHTOA, which only tells us about sine, cosine, and tangent. The S, the C, and the T are the ones that stand for sine, cosine, and tangent. Those are the abbreviations for sine, cosine, and tangent. Just kind of cuts off the end of the word or letter. And then we'll have a theta symbol, which talks about the angle. And then we have what it could equal. Okay, so the sine stands for opposite over hypotenuse, and I'll abbreviate it OPP over HYP. That's opposite over hypotenuse. Cosine stands for adjacent, ADJ for adjacent over hypotenuse. And then finally, tangent is opposite over adjacent. And so if you're wondering, what does that even mean? Let's draw a diagram of what our unit circle looks like, and specifically how it's going to create a right triangle where we can use these trig functions. So we only use trig functions with right triangles, and that's kind of what we're working with here. So I'm going to draw off to the right here a circle, which I'll call my unit circle. So here's my coordinate plane. And specifically, let's only draw in the first quadrant right now, just to keep it pretty simple, that this point here is x comma y. Since this is a radius and it's a unit circle, we know that this hypotenuse, or we'll call it a hypotenuse in a second, is 1. And then I can draw a line straight down, and of course there's already that initial side here that creates this right triangle. And theta, this angle here, is kind of what we're working with. Sometimes you'll be given what theta is, sometimes you'll need to find theta. And so we're going to write down some fractions that kind of match here. So just like based on this point x comma y, x would be the distance horizontally and y would be the distance vertically. So if I label it x and y, and then we know the hypotenuse is 1 because every radius in a unit circle is 1. So that's why it is 1. I'll just write here r equals 1 because this is a unit circle. I didn't, of course, draw up the whole unit circle that we did back on Monday, but this is just a little sketch of it. All right, so now that I know that, based on this angle here, theta, y, this side here is called the opposite side. Then we have adjacent is the side that's always closest to the angle, that's not the hypotenuse. And hypotenuse is the one where it's like the slanted one or it's across from the right angle. So that's kind of labeling all the parts there. Now I can even use those letters and numbers, x, y, and 1, and kind of find an answer here. So opposite over hypotenuse would be y over 1, which is really just y. And adjacent over hypotenuse would be x over 1, or x. And then opposite over adjacent is y over x. Now tangent is also referred to as sine over cosine, theta for both of those. So that's just another way of writing it. So we'll finish up here with just the inverse, or the reciprocal ones. So all that means, just like you know with the word reciprocal, is you flip it, right? So if I see y over 1, it's really going to be 1 over y. This is called cosecant. That's how you abbreviate cosecant, CSC, with the theta, would just be 1 over y. Because you would flip it around, it would be hypotenuse over opposite. Same thing here for secant, is abbreviated SEC, and this one is going to be hypotenuse over adjacent. So that comes out to 1 over x, which makes sense here because that would be the reciprocal. And finally, the last one is cotangent theta, which would be adjacent over opposite. And then adjacent was x, opposite was y. So x over y, that's the same thing as having cosine over sine. Okay, so those are the 6 trig functions. We're going to use these in just a minute now with our first example as we get started here on the first example, and we write down what Michigan Virtual writes for their first example and how we're going to find those answers. So it says find the value or values of all 6, like these 6 that we just found, trig functions. Now Michigan Virtual will not have you find all 6. It will just find, there's 3 different questions. Each one will just have you find 1 at a time, but it's just so we can practice once or twice. I'm going to have you find all 6 because once we can find one of them, it's pretty easy to find all 6, and you'll see when we get started here. So we are going to use the trig functions for an angle theta in standard position with a terminal ray. This is very specific because I'm copying it exactly like how it is written on the quiz, but it means the same thing. If I had just said find all 6 trig functions for angle theta, I don't have to give it all this detail, but that passes through. And we're going to do 2 examples here. So I'll call this part A. Part A will be passing through the point -8, -15, and then we'll do a part B after as well. Okay, so let's go ahead and try out this first example. The first thing I would highly recommend you do is go ahead and plot -8, -15 on a little coordinate plane to see what would my unit circle even look like. So and specifically, it explains this in Michigan Virtual in more detail, but this right triangle that we're about to draw here, it obviously we know that all unit circles have a radius of 1. What I'm about to draw here with this triangle in a second is that the hypotenuse will not be 1 because we're working with this scenario where the ray can continue for the initial side, for the terminal side. So when I plot -8, -15, this is just a sketch, right? So of course -15 probably isn't, probably even further down, but just so that you get the idea, it's from 0 to this point, which is -8, -15. I could imagine a circle kind of like this, but specifically I want to just work with this point here, okay, or this terminal ray that I just created. So a ray would have an arrow like this. So if I'm working with this, what I need to do is create a right triangle by going towards the horizontal. So just kind of going either up or down, depending on where your point is, go towards your horizontal x-axis. And when I do that, I now have a right angle there, and I have this theta. Theta will always be measured from the horizontal to wherever the, or it doesn't have to be from the horizontal necessarily, but wherever the right triangle starts. So there's theta, and so if it helps you, I would really label your sides, because to get to -8, -15 to this point, I had to go left 8, -8, and down 15. So -15 is this. If it helps, instead of looking at this triangle here, you may want to redraw the triangle like this that we kind of have right here in this diagram, just so you can see everything clearly. -8, -15, and I don't know the hypotenuse. It is not 1, because I would have to use Pythagorean theorem here to help me find that hypotenuse. I can either use Pythagorean theorem, or if I remember my Pythagorean triples, that was something that you, again, learned in geometry. One of the Pythagorean triples, if you look at 8 and 15, those two numbers hopefully are a little bit familiar. The third one was 17. That's if you memorize it. If you don't memorize it, here's what you have to do instead. So it would be using Pythagorean theorem, which is a squared plus b squared, and it equals c squared. Then we could just use a calculator if you needed to. This adds up to 289. Make sure you use parentheses around each of those numbers when you square them. And then we square root 289 and you get 13. So if C is 13, I just found my hypotenuse, positive 13 there. Or I'm sorry, it's not 13, it's 17. I looked at that wrong. So 17. That makes sense because that was my triple. So I found C. Now what also can help is, remember where theta was, it's right here. I can label from that angle where my opposite, adjacent, and hypotenuse are. Obviously this is hypotenuse, opposite is furthest away from the angle, and adjacent is next to it. So this would be written to find all 6 now: sine theta, cosine theta, and tan theta. And then we'll do the other 3 as well. So to find sine theta, remember it's opposite, you can keep coming back to this, opposite over hypotenuse, that would be -15 over 17. You are just going to leave your answer just like this. And so for Michigan Virtual, you'll look for whichever one of the answers they want. If it said, not, they won't say all 6, it would just say find sine or find cosine, or whichever one it is, that's what you're looking for. Cosine here would be -8 over 17. And then tan theta would be opposite over adjacent, which is -15 over -8, which simplifies to 15/8. Okay, and then you would do the same thing for cosecant. These are easier because you can just look at your answers and flip them. So -17/15, it doesn't matter where you put the negative. Secant would be -17 over 8. Again, does not matter where you put the negative. And then cotangent theta would be 8 over 15. They're both going to be, again, they were both negative, but then of course turns into a positive. So I did have a second example, but just to keep this a little bit short, the video not too long, I'm just going to maybe tell you what an example is. You can try it out, and I'll write down the answers so that you can always try it out. If you have any questions, you can come in the afternoon and I can walk through this example with you. The question was for the ordered pair 3, -5, and here are the answers. Sine theta was -5 over square root of 34. So again, you could pause the video, try this one out, and then just check your answers right now. If you don't end up getting them correct, then please come in the afternoon. I'd be happy to help you. So this is 3 over root 34. Then we had tan theta is -5/3. So those are the three that are the trig functions. Here are the reciprocal trig functions. You just flip them upside down. So square root of 34 over -5. Secant would be square root of 34 over 3. And finally, cotangent would be -3/5. So you will need to find the square root of 34 that shows up here. You would do, again, a squared plus b squared equals c squared. Here, this one is not a Pythagorean triple, and it's not a perfect square like 17 like this. So that's where we get that square root of 34 from. But again, try this out. If you had questions, again, come in and we can go over them. All right, so that's one type of example you're going to see on the quiz. The next two things are two different types of angles. One's called coterminal angles, and another one is called reference angles. So I'll kind of define that right on the bottom here, and then we'll go to the next page to try it out. So a coterminal angle, or coterminal angles, are angles that have the terminal side in the same location. Remember, what terminal side is just the when you're drawing where your unit circle ends, from where it starts at the initial x-axis and then where it ends. So angles that have the terminal side in the same location. So if we think about this, say you have a unit circle. I'm just going to show you even this one, for example. If I have a unit circle like this where I have this point here, and it might give me the angle measure for how many degrees this is, or how many radians this is. So if it's at something like 215 degrees, that location right here, this angle, if I wanted to find a coterminal angle, what that means is you could basically do another rotation around or revolution around it and end up at the same location again. And it would, in order to do that, I would just be adding 360 degrees because that's one full circle. I could also subtract 360 if I want to go backwards and come around. So that's kind of the idea here, is it's basically going to be adding or subtracting 360 degrees. Now, what if it was in radians? Then we would write 2 pi radians, because that's how many radians to go around one circle. So we are going to do that as many times as we want to or need to. I'll show you an example where sometimes we need to do it a bunch of times. But we can, again, every time you do that, it is then called a coterminal angle. So for example, if this angle was 200 degrees, I go around 360 one time. 200 plus 360 would be 560. I could go around one more time, add 360 again and see what that comes out to, and so on. I could also keep subtracting 360, and I could get negative coterminal angles as well. That's absolutely fine, because it would again give you the same exact location. As long as it's ending up in the same spot, that would be considered coterminal. Now, of course, they can give you different experiences, because imagine if you are doing a spin. If you spin once versus spinning 5 times, even if you end up in the same spot each time you do it, 5 spins is going to definitely feel a little bit different. You'll feel maybe a little bit dizzy, but that's kind of the idea with coterminal. So let's go ahead and practice the example that Michigan Virtual has on the quiz for this type of angle. And it's worded a little different. It doesn't really say coterminal, because, and I wish it had, because it kind of would remind you of what to do. But here's what example 2 says here. And again, your questions may be in a different order, but the question will say something like, find an angle in the normal range. And that goes on to tell you what is the normal range, 0 degrees to 360 degrees. That would be in radians, or 0 radians to 2 pi radians, That's like what they're considering, obviously, the normal range, because that is, when you think of the unit circle, that's what all the possibilities are, whose terminal side points in the same direction as the terminal side and I know this is, again, very wordy. This is just what they have as their question. I wish it just would have said find the coterminal angle, but it means the same thing. So same direction as the terminal side of an angle measuring, and then I again have a couple of parts here for you guys. So part A will do one angle. I have a total of 4 here, just so that we can get a variety. So we have 800, A is 850 degrees. So if that's the angle measure given, and we want to make it so that we land on the same location as what 850 would be if I was to draw it out onto a unit circle, and 850 is a lot larger than 360. So in order to figure out what that would be, I could keep subtracting 360. So since this number is bigger than 360, we're going to subtract 360 each time, not add it, because it would get larger and larger. Now you could add it if you wanted to, but I can probably tell you that on Michigan Virtual's like answer choices, we don't want to add it because we need to end up in this range from 0 to 360. So the only way to move forward here is by subtracting, because we need to get an answer between 0 and 360 degrees. This isn't degrees. So we start by subtracting 360 once, and you get 490 degrees. That's not in between 0 and 360. So I have to do it again. 490 minus 360 is 130. That works. 130 degrees is our answer here, because we needed to find an angle that's between 0 degrees and 360, and that definitely is. So we had to subtract 360 twice. Here's another one. Same idea, but let's imagine our angle is negative 115 degrees. So we would start by adding 360 this time, because we're trying to get out of the negatives, and we have to again get to an answer between 0 and 360 degrees. So negative 115 plus 360 is 245. And so that's my final answer. It's that simple. Just either add or subtract 360 so that you end up in between 0 degrees and 360. Now it gets a little bit harder with radians, just because we're dealing with pies and so on, and fractions. So letter C, let's say we had 22 pi over 3. So kind of looks a little tricky, because if you think about the unit circle, or if you need to look at an example of the unit circle, one of the last spots towards the end, like when you make a full circle around, if it has a denominator of a 3, the last one was like 5 pi over 3 in the 4th quadrant. But I'm trying to get to 22 pi over 3. So this is a lot of revolutions around, because one full circle is 6 pi, right? So one circle in radians is 2 pi. I'm thinking how I would write that in this fraction form that has a denominator of a 3. We know that 2 pi is the same thing as 6 pi over 3, right? If you want the same denominator. So what we're going to do here is we're going to keep subtracting 2 pi, just like I subtracted 360 degrees, but now that this is in radians, I'll keep subtracting 2 pi. And the easiest way to subtract 2 pi is to actually subtract 6 pi over 3, because they're common denominators. So 22 pi over 3 minus 6 pi over 3 comes out to 16 pi over 3. And if you're thinking, well, is that good enough? Is that my answer? You can double check that. Remember, one full circle around is 6 pi over 3. So it needs to be, the answer needs to be less than 6 pi over 3, or equal to it, but it won't be in this case. But let's go ahead and keep going. So 16 pi over 3 minus, again, 6 pi over 3. This is 10 pi over 3. Still too large, because, again, we have to be less than 6 pi, where it's 10 pi. And finally, if I do it one last time, though, it should work, because 10 minus 6 is 4 pi over 3. That is the final answer. So you get to a point where, yes, my answer is less than 6 pi over 3. That's it. So if I was to graph where 4 pi over 3 is, it would be in the third quadrant. And this 22 pi over 3, if you were to rotate it 3 more times around, you would end up at the same spot in the third quadrant where 4 pi over 3 is. All right, let's try another one. The last one, I just wanted to show you a negative in radians, so negative 11 pi over 6, how that would look. So same idea as the last one, but you have to think of, what am I adding? Remember, adding, in this case I'm adding because it's negative, but I want to add 2 pi. But adding 2 pi to this denominator of a 6 would be tricky. So again, I would recommend writing it with a 6 in the denominator. That would be 12 pi over 6, because that's 2 pi. So let's go ahead and add 11 pi over 6 with 12 pi over 6. And that's just 1 pi over 6, which we usually don't write that 1. We can just call it pi over 6. That's the final answer on that one. So again, radians tend to be a little bit trickier, but keep either adding 2 pi or subtracting 2 pi. Same idea as adding 360 or subtracting 360. But that's what you're going to keep doing over and over again until you get to a point where it's in the normal range. All right, so the last type of example, or before we get to the last example, you have to know one more type of angle, which is called reference angle, or reference angles. And so reference angles are angles, or an angle between the terminal side and the x-axis. Okay, so remember where that is. I'll draw a little sketch real quick. It could be like my unit circle. Anytime I'm working with a reference angle, let's say I have this angle here, or this point here on the unit circle. The reference angle would be when I can draw a line going towards my x-axis. So drop down or up, depending on where your location is. You need to either go up or down only towards the x-axis. Remember, this is our x-axis, horizontal one. And so once you get to that, you now have to find the reference angle. So the reference angle is the angle that goes from, like, it's this degree measure or angle that we're working with right in there. It's kind of how far away is it from the horizontal. It's always going to be measured from the x-axis, though, not any other axis. But again, that's our terminal side, like it says, and then this is our x-axis. So that could be how we find the angle there. What if one of my points was here instead? Same idea. There's theta, and that's my reference angle that I want to find based on this diagram. Again, I would base it off this segment here, or the x-axis. Remember that the x-axis here, we come back around and it's at 360 degrees, or it starts at 0, and then this one is at 180 degrees. Or if you want to think of with radians, that's pi, and this can be 2 pi. Right, so let's work with this concept as we find some reference angles. It's basically just a lot of either subtract, if either from 180 or from 360. Those are the only two numbers we're going to subtract from, not from 90 or 270. Because again, I don't care about that vertical one. I only want to measure from the x-axis. So here's our first question, or the last question, example 3. Where in Michigan Virtual it says it pretty straightforward, just like it should be. I'm just going to say find the reference angle for an angle measuring. And then here are a couple of, I have 3 problems that we can try out. 305 degrees is the first one, just to start with a positive number. And again, it can help if you visualize where is 305, because I would highly recommend drawing a little sketch of this so that you can decide, well, what am I going to add or subtract, or what number am I subtracting? So 305, if you think about the quadrants, remember 180 is here, and then there's 270 at the bottom, and this is 360. So 305 would have to be in the 4th quadrant somewhere. It doesn't have to be precise, like nothing exact, but we're trying to find out kind of its location so that you can find the angle to the nearest x-axis. So to the right side or to the left side, this would be too far. So here is my reference angle. So I need to measure that distance, or that, not distance, but angle measure between 360 and 305. To do that, I just need to subtract. And so 360 minus 305 is 55, so that is the reference angle for 305 degrees. It's not saying coterminal angle, make sure you don't mix up the two. Coterminal is where you have to either add or subtract 360 degrees. Here, reference angle, you're saying how far away is it from the x-axis, whichever x-axis we need to look at, the positive or the negative. So let's see another one. What if it was not in this location, but let's say it was at 132 degrees? This one, if I was to plot this on my coordinate plane again, or my unit circle, we know 90 degrees up here and 180 is to the left here. And so 132 would fall somewhere in here. All right, so if that's the case, I now need to measure not all the way from here to here. That would be too much. I just need to know this angle measure here. From 132 to 180, that's my theta I'm looking for. So 180 minus 132 is 48. So 48 degrees would be our answer there. All right, last one is going to be in radians, and then we are all set here. So letter C is 5 pi over 3 is what's going to be given to us. So you have to think about, or maybe look up the unit circle if you don't remember exactly where 5 pi over 3 is just yet with radians. Eventually you do need to memorize that. Those of you moving on to pre-calc and honors pre-calc, you'll need to really know these pretty well. So even though we didn't do time tests and things like that we would have in person, you should kind of hold yourself accountable and try those out. All right, so here is a diagram where if you think about where 5 pi over 3 could go, just to remind you, remember this is pi. Well, if I want a denominator of a 3 there, that's really the same thing as 3 pi over 3, because remember the 3's would just cancel and you'd have pi right here. So if I keep going somewhere in this quadrant here, I'll have 4 pi over 3. Now this right here is not 5 pi over 3. If you think back to what it was, it has a denominator of a 2. It's called 3 pi over 2, so there's nothing there. So 5 pi over 3 would be somewhere here in this quadrant. And again, I don't need to know exactly where. As long as I know that's 5 pi over 3, I need to find this angle measure to the nearest x-axis, which would be this one here. And we know that this is 2 pi when it comes back around, but 2 pi could be written as 6 pi over 3 if I want to get common denominators, so that I can subtract 6 pi over 3 from, or 5 pi over 3 from 6 pi over 3, and I'll be left with my answer, which is pi over 3. That's this whole distance here, which makes sense because I'm that much away to get to 6 pi over 3, which is 2 pi. All right, and that's pretty much it. If you have any questions, please consider coming in the afternoon today, or we can also do it on Friday. Have a great day, and I will see you on Friday in Zoom.